Welcome to the first outcome, where we turn a wall of numbers into a picture. We'll build stem and leaf diagrams and box plots, then read the story they tell about the shape of a distribution. Think about a list of 40 exam marks. Stare at the raw numbers and your eyes glaze over, but plot them and the shape jumps out. A good diagram answers 3 questions at once. Where's the center? How spread out are the values? And is the distribution lopsided or hiding anything odd? That's exactly what we're after with real data like exam marks, GP waiting times, or a shop's daily takings. Before we draw anything, let's get the vocabulary straight. A distribution is just the pattern of how often each value shows up. Raw data is what you jot down in the order it arrives, while ordered data is that same list sorted smallest to largest, which is nearly always your first move. And frequency is simply a count of how many times a value or a class turns up. Here's the clever thing about a stem and leaf diagram. It sorts your data, but keeps every single original value in view. You split each number into a stem, the leading digits, and a leaf, the final digit. So the mark 41 becomes a stem of 4 and a leaf of 1. And you always add a key, something like stem 4. Leaf 1 means 41. Turned on its side, it reads like a bar chart, so the shape is easy to spot. Building 1 is a 4-step routine. First, order all the values from smallest to largest. Next, choose your stems, usually the tens digits, and list them down a column. Then write each unit's digit, the leaf, beside its stem, keeping them in order. And finally, never forget the key that tells your reader a stem of 4 and a leaf of 1 means 41. Let's look at 20 exam marks sorted into one of these. Each row gathers all the marks in a given 10. So the 60s row shows 61, 62, 64, 66, and 67, 5 marks bunched together. Because that's the longest row, you can see at a glance that most of the class scored in the 60s. And nothing's been lost. Every original mark is still sitting there to be read off. Now let's actually read some summary figures off those 20 marks. The lowest is 41 and the highest is 92. So the range is 92 minus 41, which is 51. The modal group is the 60s, with 5 marks the most common band. And with 20 values, the median is the average of the 10th and 11th. That's 64 plus 66 all over 2, giving 65. So the class centered around 65%. A solid performance with just a few high and low tails. Suppose you want to compare 2 classes rather than describe just one. A back-to-back stem and leaf shares a single column of stems, with one class's leaves growing off to the left and the others to the right. Say Class A on the left and Class B on the right. Now you can line up their centers, their spreads, and their shapes side by side and see straight away which group has the longer tail. To describe spread properly, we chop the ordered data into quarters. The median, sometimes called Q2, is the middle value splitting the data in half. The lower quartile, Q1, is the median of the bottom half, with a quarter of the data below it, and the upper quartile, Q3, is the median of the top half, with 3/4 below it. The gap between them, Q3 minus Q1, is the interquartile range, the spread of the middle 50%. A box plot, or box and whisker plot, draws the 5-number summary straight onto a number line. The box stretches from Q1 to Q3, with a line inside marking the median. Whiskers reach out to the smallest and largest values that aren't outliers, and any genuine outliers get plotted as separate points beyond them. Because the box holds the middle half of the data, its width is exactly the interquartile range. Drawing 1 follows 4 steps. Start by summarizing. Find the minimum, Q1, the median, Q3, and the maximum. Draw the box from Q1 to Q3 with the median line inside. Add whiskers out to the lowest and highest values that aren't outliers. Then mark any outlier, anything beyond 1.5 times the interquartile range, as its own separate point. Let's work a real one. GP surgery waiting times in minutes for 11 patients. With 11 values, the median is the sixth one, which is 27 minutes. The lower quartile is the middle of the bottom 5, 18, and the upper quartile is the middle of the top 5, 36. So the interquartile range is 36 minus 18, which is 18 minutes, the spread of the middle half. Every box plot starts from these 5 numbers. Now picture that plotted. The box runs from 18 up to 36, with the median line at 27. The left whisker reaches down to the minimum of 12, and the right whisker out to 40, the largest ordinary value. But one patient waited 70 minutes, sitting far off to the right as an outlier. Notice the median sits left of center in the box, a hint that the data is skewed to the right, a typical wait of about 27 minutes with one unusually long one. So, which display should you reach for? A stem and leaf keeps every raw value and works beautifully for small or medium data sets, showing shape like a sideways bar chart. A box plot throws away the detail and shows only the 5 summary numbers. But that's exactly what makes it brilliant for comparing several groups at once. Both reveal shape and both flag outliers, one in the tails, the other as separate points. Skewness is just a word for whether a distribution leans to one side. If it's symmetric, both tails are roughly equal, and the mean and median sit close together. Positive, or right, skew has a long tail of high values, dragging the mean up above the median. Negative, or left, skew has a long tail of low values, pulling the mean below. Real data is rarely perfectly balanced, so naming the skew is a genuine interpretation skill. Picture 3 curves side by side. On the left, negative skew, with the tail stretching away to the left. In the middle, a nice symmetric hump, balanced about its center. And on the right, positive skew, the tail trailing off to the right. Incomes and house prices are the classic right-skewed example. Most people cluster fairly low, while a handful of very large values stretch the tail. Naming the skew tells you how honest the average really is. Here's a neat rule for positive skew. The mode is below the median, which is below the mean. Those few extreme high values haul the mean towards the long right tail, while the median barely budges, which makes the median the fairer average for skewed data. It's exactly why the Office for National Statistics reports median household income rather than the mean, since a wealthy few would otherwise inflate the figure. Comparing the mean and the median is a quick test for skew. You can read skew straight off a box plot from where the median line sits. If it's slap in the center with equal whiskers, the data looks symmetric. If it's pushed close to Q1 with a longer right whisker, that's positive skew. Close to Q3 with a longer left whisker, that's negative. In our waiting times plot, the median sat to the left of center, so the data was right skewed, just as that 70-minute wait suggested. An outlier is a value sitting far from the rest, one that can distort your summaries if you're not careful. The standard way to pin one down is the 1.5 times interquartile range rule. Anything below Q1 minus 1.5 times the interquartile range, or above Q3 plus 1.5 times the interquartile range, counts as an outlier. Those two cutoff values are called the fences. Let's test our waiting times. The interquartile range was 18. So 1.5 times, that is 27. The lower fence is Q1 minus 27. That's 18 minus 27, which comes out at minus 9 minutes. The upper fence is Q3 plus 27, so 36 plus 27, giving 63 minutes. The 40-minute wait sits comfortably inside the fences, so it's a normal value, but the 70-minute wait is beyond 63, so it's flagged as a genuine outlier. Nice and objective, no guessing. Why does all this matter? Because an outlier might be a real extreme, a typing error, or a special case worth a closer look. That 70-minute wait could be a one-off emergency, a recording slip, or a real sign the service is struggling. Outliers and skew both drag the mean and the range away from the typical experience, which is why the median and interquartile range describes skewed data more fairly. And the golden rule: never just delete an outlier, investigate it first, and report what you find. This leads to a useful split between measures that resist outliers and those that don't. The median barely flinches when you add an extreme value, and the interquartile range ignores the extreme quarters entirely, so both are your friends for skewed or outlier-prone data. The mean and the range are the opposite. The mean gets tugged towards a single extreme, and the range is defined entirely by the two most extreme points. Save those for roughly symmetric data with no outliers. So, pulling the outcome together. Stem and leaf diagrams sort your data while keeping every value, and they always need a key. The 5-number summary, drawn as a box plot, gives center and spread, with the box width equal to the interquartile range. Skewness names the direction of the longer tail. In positive skew, the mode is below, the median is below the mean, so the median is the fairer average. And the 1.5 times interquartile range rule flags outliers, which you investigate rather than delete. That wraps up constructing and reading diagrams of distributions, from stem and leaf plots and box plots through to skewness and the outlier test. If you'd like to shore this up, Rowntree's Statistics Without Tears is a gentle read, while Crawshaw and Chambers goes deeper with worked examples, and Corbett Maths and BBC Bitesize both have handy walkthroughs. It's well worth browsing an ONS release on the distribution of weekly earnings to see this skew in genuine national data. Have a look at the ebooks and journals on the Moodle, and bring any questions to your tutor before you tackle the assignment.